All right, so we're getting to energy. Right? Now, this is a new variable, a new unit. It's going to be a new way to think about physics, a new approach. Okay? And what you'll see, like using like energy conservation methods that we're going to get into, is that we can set up and solve problems, some problems that we didn't really have a good way to solve before that now we can't solve. And some problems we're going to solve that you technically do at this point have alternate methods to solve, maybe just kinematic motion, or you could go through dynamics. Okay. But sometimes going through energy and energy conservation is actually a lot easier and a lot faster to solve these problems. Okay. So let's start with the basics here. Okay. What is energy? Well, I can quantify, you can measure, quantify energy in joules. Okay. There's some other forms you can quantify also. You could do kilowatt hours, technically works. I'll probably talk about it tomorrow. British thermal unit, sometimes you see, but for this class, we care about joules. And the unit for this is capital J. Capital J is joules. Okay. Well, what is 1 joule? Because you guys know what a kilogram is. Here's a kilogram. You guys know what a meter is. Here's well, about 0.3 meters. You guys know what a second is. Tick tock. So you guys know what force is in newtons. You guys know what a newtons. Okay, so what the heck is a joule? How does it relate to those other variables? Okay. So 1 joule breaks down into 1 Newton times 1 meter, 1 Newton meter. Okay, so now we're back onto like safe ground because you guys know a Newton of force, like pushing or pulling. Okay, and you guys know what this is. Okay, so if you push something with 1 Newton of force for 1 meter, then it's like you've transferred 1 joule of energy into it. Okay. Let me go one step further because Newton is a composite unit. So you can break this down ultimately to, because Newton is kilogram meter per second squared. You guys remember that? F equals ma, Newton's second law of motion. And if you combine that with this meter here, ultimately you get kilogram meter squared per second squared. Okay, so that's what 1 joule of energy is, right? Okay, so talking about energy, here's how you can quantify, measure it. Okay. And what's particularly interesting is that energy is conserved both in the universe, okay, but also in any closed system. Okay. So however much total energy that there is in the universe is the same energy that there's been for the last 14 billion years and the same that there ever will be. Right? Now, in the future, like spring semester, we'll talk about a different type property, which is called entropy, which is kind of like, you can think of like the quality of energy, and that actually does change with time. But the actual quantity, like the number of joules that have been around, right, same as there's ever been. It's maybe sort of asterisk on that. You could have some mass energy equivalent when you get to nuclear energy, but still, it's still kind of conserved, right? So basically, you can't create or destroy energy. Right? It's like there's a lot of energy like powering stuff in this room. There's lights, there's air conditioning, there's projection. Right? Well, where did that energy come from? You just can't create it out of whole cloth. Right. Well, see, it's coming from the electric grid, which is coming from a power plant, which is coming from like whatever energy sources. Probably a lot of it's fossil fuels. Probably about 20% of it's from nuclear. So what you can do is you can transfer from one object to another, from one system to another. Okay. Let me go hit this term right here: closed system. Right. So what do we mean by a closed system? Okay. Closed system is where there's no energy transfer, also called work, into or out of system. Okay. So if you have like some system roped off, there's no energy being put into or out of it, then however many joules of energy are in that system, that's like a constant number. Okay. Another kind of perspective on closed systems is you could say this, that there's no net external force. Right. And sort of one implies the other, right? So if something is pushing on the system or pushing on an object, like some kind of external force, right, for some distance, well, and that it just opens it up to some kind of energy transfer. So kind of different perspectives there. Right? Now, speaking of closed systems, closed system. Okay. Let me write this down more in a physics type way. I can say this: the sum of energy initial is equal to the sum of energy final. So let me spell this out. The sum of initial energy is equal to the sum of final energy. Okay. That's what conservation of energy is, right? Energy is conserved. You can't create or destroy it. So however much energy it was, it's the same as there will be. Okay? This is the framework we're going to use to solve a bunch of problems. And just think ahead a few steps here. Okay. Where I say the sum of energy, well, energy can take different forms. It can take these forms and some other forms too, but these are like some mechanical forms. Okay. And then you can substitute these different types of energy into, like, this might be this plus this plus this. This might be this plus this plus, right, different types you could add together. Okay. It has to equate. Okay. Now, a closed system might be in contrast to an open system. Okay. System, right? If the system is open, well, it's just kind of the opposite definition of this, right? So now there can be an energy transfer entry out of the system, and there might be an external force, possibly doing work on that system, right? So I might just modify this by this. I'd say the sum of energy initial plus the work done on the system. So work done on the system equals the sum of energy final. Okay, so if you have like 10 joules of energy to start with, you did an extra 3 joules of work, 10 plus, or is it, there were 3 joules of work done on the system. 10 joules plus 3 joules is 13 joules. Okay, so there you go. Okay. Okay, so far. Okay. Now let's get into these building blocks that I'm talking about. Okay. So forms of mechanical energy. If you ever hear me this week use the term building blocks, that's not exact like physics term, but kind of a Griffin term for we're going to like construct these conservation of energy equations, right? And I'm probably going to be referring to one or multiple of these. Okay? So this is a pretty good list of just mechanical energy, types of mechanical energy. Energy can take different forms, right? But there are some types of energy that we care about for solving problems in this class, and some that we, well, not so much. Okay. And so, I mean, all these qualify. We're going to solve a bunch of problems with these. But like some counter examples might be like energy stored in a battery, like chemical energy, nuclear energy. We're not going to get to until next semester. Even like there's energy. Well, okay, yeah. So those types of thermal energy. How about that? Right? If you like heat up a glass of water. Okay. And so let's start with this one, work. Okay. Now, really, work is really just like a transfer of energy. Okay. I can represent it with the character capital W. Okay. So this is a transfer of energy. Right. Now, this character capital W, be kind of careful with this because here I'm showing it as a variable. Right? Capital W is a variable, represents work. Okay. But tomorrow you might see capital W as a unit that represents watts. Like you ever look on a light bulb, it says like 20 watts, 20-watt light bulb. Right? And that's a completely different concept that could quantify power, but that would be as a unit. But here you're seeing it as a variable. Right? Let me spell that out. This is as a variable. Work. Right. And what's the formula for work? So work, you say capital W or just spell it out. Okay. Is equal to force times distance. Right? So this is force, capital F is force, you guys know that. D could be distance. Okay. And this dot right here, right, means that this is actually a special kind of multiplication called a dot product. Okay. And what a dot product means is that you only multiply parallel components. Okay. Okay. We give you guys sort of a modified version of this, and then we'll do an example. Right. So, right. Some textbooks might say this: work is force, the magnitude of force times the magnitude of the distance moved, okay, but only times the cosine of the angle between those two. Okay. That's the same thing. It's another switch. Dot product the same way as just multiply the magnitudes and times the cosine of the angle between them. Okay, so let's go through some examples. Okay, guys ready? Okay. So let's start with lifting a textbook. About that, lift a textbook. Okay, so I got this textbook. You guys got there? Okay, and let's do a quick free body diagram on this guy. Right, so this textbook, let's say it has a mass of like 1 kilogram, which would be equivalent to this. So I have a book that weighs just as much as this weighs. Okay, and therefore its weight would be about 10 newtons, right? 10 Newton weight. Right? Now that's like if I drop the book off a cliff, that's what the free body diagram looks like. But maybe I'm holding the book. Okay? Maybe I'm holding it. Okay? So there's like a lifting force, F sub lift, right? Which should also be like 10 newtons, right? Like if either I'm holding the book at rest or if I'm moving it with constant velocity. Okay? And looking at that free body diagram, it might be either one of those, right? I might be holding it at rest or I might be moving up at constant velocity. Okay? Now let's take the moving upward situation. Now let's say I move this thing up some height. Let's say a height of 3 meters. Okay? So I'm applying an upward force that's balancing out its weight, okay? And I'm lifting it this many meters. Okay? Well, wouldn't it take energy to do that? To like lift the book? Okay. So the work done lifting the book is force dot distance, right? And in this case, they're all parallel, right? So I'm lifting straight up and it's moving straight up. And so you just multiply them together. Okay. So the work would be a 10 Newton applied force, that's this 10 newtons, okay, and a distance of 3 meters. Right. Put that all together, that's 30 joules of work. Okay, so like transfer 30 joules of work, 30 joules of energy into the book, right, lifting it. Okay. Suppose you had a mechanical device that ran on batteries. Do you guys think that battery has like a finite amount of energy stored in its chemical bonds? Okay. And then you could run the battery for so many operations, maybe it runs out after a year or two. Okay. So it extract this much energy out of the battery. Okay. Or suppose you have an electric appliance, you plug it into the wall, and it's kind of lift this thing. Okay. And then you have to pay a utility bill, right? Because the utility company says, "Oh, now usually they say like how many kilowatt hours do you do?" But you could translate that at some number of joules, right? Maybe you owe like 5 cents to the utility company. You have to pay for those 30 joules to lift the book. Okay. Right, something like that. Okay, how about this? Okay, let's say let's have the same book, and now I'm going to move the book horizontally across the room. So same textbook. Right? It might have same looking free body diagram. Right? It has a weight of like 10 newtons, has a lifting force. Well, that would also be 10 newtons, wouldn't it? Right? You have to hold it up. Okay? And then I'm going to move this across the room. Okay. So horizontally, let's do the same distance as before, but just be horizontal, right? Like 3 meters. Okay. Well, how much work was done doing this? Right? Well, if you pull out your formula, work is force times distance. But remember, it's a dot product, right? That's got to be important. Right? So I see the applied force is still 10 newtons, right? Holding up 10 newtons. But the distance it moves is actually like perpendicular to that. You see that? Okay. So the fact that this is a dot product, remember, I'm only multiplying together parallel components, but if they're perpendicular, there's nothing that's parallel at all. So the way that I'm pushing it and the way that it's moving have nothing to do with each other. So what's the answer? How many joules of work did I do moving the book across the room? 0. 0 joules. 0. Okay. Now let me break out the more granular version of this. Work could be force times distance times cosine of the angle between them, right? Pop in some numbers. So I got my 10 Newton force. Yeah, sure, it went a distance of 3 meters, right? But that 10 newtons and those 3 meters are at 90 degrees to each other. Okay. And oh, what's cosine of 90 degrees?
Zero.
Yeah, 0. 0 joules. Okay, if you want to spell it out. Okay, guys good? Yeah.
It's only 0. Aren't you still applying energy to it?
Maybe you have to like get it started, maybe a tiny energy to like get started in motion. But suppose you did, like once you get it in motion, doesn't law of inertia for slow motion say it just wants to keep going, right? Until you apply another force to bring it to a stop, right? So yeah, so suppose it like was in motion and you just like lifted the book, right? It's already moving across, and lifting it has nothing to do with its lateral motion. Yeah, so that force doesn't actually move the book, right? It's a like yeah, maybe a lateral force to get it going, but it's the motion. Yeah, you don't actually need any energy to get it going. All right. Okay, so we got lifting the book. You're putting work into it that takes energy. Right? Moving the book laterally. Well, the force and the distance are perpendicular, so it's a wash. Okay? But what about got like a third example lined up? Okay. Let's say you were like pushing a shopping cart. Maybe I should have stuck with the book. I don't know. I like the shopping cart, so we're gonna go with the shopping cart. Okay. Got little wheels here. Oh, it's on the floor. Okay. Here's like the center mass sort of. Let's get a parallel line right here. Okay. And let me do like a partial free body diagram. Suppose I'm pushing, not exactly horizontally, but kind of like down and forward at the same time. Okay. And let's have that F push, that applied force be, let's say 50 newtons. And I'm going to say the angle it is below the horizontal is 37 degrees, which I hope you recognize. You guys have seen that angle many times in this class, right? Okay, you guys know I'm setting up on a what triangle? 3, 4, 5, right? Because 3, 4, 5 right triangles supposed to have that angle, right? It's like 36.9 degrees. You guys get the idea, okay? Okay, so that pushing force, okay, part of the pushing force is actually pushing the cart forward. And part of the pushing force is not, right? It's just pushing the cart down even more. Okay. Now that's a partial free body diagram. Maybe this cart has some other forces that I don't care about so much. It probably has a weight. It probably has a huge normal force, right? I mean, now that I'm like pushing down even more, right? The force on the floor has to be huge compared to its weight, right? Right. There may or may not be a friction force. You know, think about that later, right? So there might be, but it's something like that, right? So if I ask the question like, how much work was done pushing the cart? How much work was done pushing the cart? Right. Well, let's break out the formula. Work is equal to force times distance, force dot distance, which is force times distance times cosine of the angle between them. Okay. Now, if you just plug in these numbers, okay, so I got an applied force of 50 newtons. Okay. And when I forgot to give you guys a distance. Okay. Let's send this a distance of 7 meters. How about that? Distance is 7 meters. Okay. So 7 meters. Okay. And cosine of 37 degrees. Right? Or if you like, cosine of 37 degrees, you guys already told me that's like 4 this because 3, 4, 5 right triangle, right? If you put this all together, okay, so let's put this together in a particular way because there's a better thought process I like. Okay. The fact that the cart moves forward is like to the right on this paper, right? Moves forward. Okay. Isn't it true that only the forward component of your force is actually putting any work into the cart? Like this doesn't do anything. Okay. This does. Okay. So I'm thinking this right here is 40 newtons. Do you guys like that? Which would be 4/5 of 50. Okay. Or if you like, how about this? What is 50 newtons times cosine of 37 degrees? Now it's not exactly 37, it might be 36.9. You guys get the idea. Okay. Let's just round that to about 40 newtons. Is that okay? About 40 newtons. Okay. So 4/5 of 50 newtons, that's the component of the force that's even doing anything. So I'll go ahead and tag these two together. Right. And I do that for 7 meters. You guys see that's going to be 280 joules worth of energy. Right. So there's been 280 joules transferred into that shopping cart. Okay. So okay. Okay. Now what? Because you could take this problem further. You could say, well, what does that mean? Right. That might be one of a number of things. Suppose this friction did not exist. If there was no like friction force, right? Then all that energy would transfer into its motion, which would be like kinetic energy, it'd be like speeding up the cart, just going faster, faster, faster. Shoo. So you push on the cart and it speeds up. Right? Suppose there is a friction force. What if the friction force is bigger than I drew it, and the cart doesn't actually speed up at all? What if the friction force is so big it actually counters this out? So the cart just goes at constant speed. Okay. Well, in that case, the cart it's not speeding up, so this has nothing to do with that. Well, what you could say is that you put 280 joules worth of energy into it. You did 280 joules worth of work on the cart, but the friction force zapped out 280 joules from the shopping cart, so there's no net change. And then it's just back to like the book moving across the room where there's zero net force, there's zero net work being done on the shopping cart or the book. Okay, is that okay? Okay. All right, so we're like pushing this cart around. We've got the book, we might be lifting the book or move the book across the room. Let's go back to the lifting the book situation. Okay, so lifting a textbook, because this is a perfect segue into the next type of energy that I want to talk about. Okay, so let's take this story. Right, you lift the book. You know, if the book weighs 10 newtons, you have to apply 10 newtons. Lifting force, suppose you do that for 3 meters, which is approximately the height of this classroom. Right, so you set it on top of a really tall shelf. Right, you did 30 joules of work like moving the book. But hang on a minute, if energy is not created or destroyed, that 30 joules is sort of like embedded in the book. Right? And I know that because suppose the book's like sitting on a shelf and I give it a tiny tap. Right? When you get all that energy like back in the crash, like what was the energy associated with like crashing? Right? Well, it has something to do with the weight of the book, but it also has something to do with like how high it fell from. Right? So that 30 joules is sort of like always there. But you did 30 joules of lifting, like lifting the book. Right? And that 30 joules is sort of like still embedded in the book. Okay. So let's go back to this. So here we got really tall shelf. Okay. And here's this book like perched on the edge of this really tall shelf. So there's our book. Okay. And I can call that energy that's still stored in the book. I can give it a name. I can call it potential energy, or more specifically, gravitational potential energy. Okay. So I've been trying to use capital U. That's really what I've been doing like last few years, using capital U to represent this. Or specifically, I can throw a little subscript G on it for gravitational. Although that's a 5-syllable word, so sometimes I might just say potential energy, but you guys get the idea, right? There's another kind of potential energy we'll get to later. Okay. But if you see some of my old materials, you might see PE for potential energy, or Paul Hewitt, I think, also uses PE. Right? So if you ever see that, okay. All right. And let's think that I bet we can piece together a formula for this, right? Because let's see, this book has some mass, right? I mean, it also has some weight, doesn't it? Because it's in a gravity field, right? And it's been lifted some height above the floor. So I can call that height H. Okay. And suppose you did amount of work lifting it that was equal to its weight, for lifting force, right, multiplied by height, right? And that energy is now like effectively like stored in the book, right? So again, give it a tiny tap, it crash lands. Right? How much energy is that? So I'll do U sub G, potential energy is, right? Well, it'd be its weight, which is mg, times the height above the floor, which is h. Right? And now you have a new expression. Right? There's the energy stored in height. Right? I'm going to say this is localized. Right, for here, I'll tell you guys what that means too. Okay. So here, let's run a quick example. So for example, suppose the mass of the book was 1 kilogram. It's in a gravity field of about 10 meters per second squared. And we lifted it 3 meters. Right? Then the potential energy, gravitational potential, would be mgh, 1 times 10 times 3. Oh, there's your 30 joules again, right? It's like the same thing. Is that true? Okay. Now, what do we mean by localized? All right. Well, I mean like localized to the surface of the Earth. Right? And let me throw you some ideas that see, like when I first learned this way back in the day when I was a student, this formula I couldn't buy immediately right away. I was kind of confused about this, and I'll tell you guys why. Okay. One thing is, here, take a look at that H. See that height right there? That height, that assumes that this right here is the floor. Right? Wouldn't this be like the defined height 0? H equals 0 meters. Okay? I mean, as long as you define that in 0 meters, then those works out okay. Like it's the height above that. Okay? But you could very quickly change that, couldn't you? Because aren't we on the second floor of the building? Okay? What if I just dig a hole in the floor right here? Right? Just like dig a hole right there. Okay? And then do the same thing. Give us a tiny tap, tap. Okay. Well, now it's not just going to fall H. It's going to fall like through the floor and down to the first floor way below us, which is like much bigger than that. It might be like 3 or 4 meters taller. Okay. So that throws completely out of whack. Okay. And how it ends up being okay though, right? It ends up being okay, right? So mathematically, if you treat this, say I define this as height 0, right? The book could fall through the floor and go to a negative height. And when you set up the equations and you solve stuff, you can treat heights as going negative beneath the floor, and everything mathematically works perfectly fine. Okay. Or what you could do instead is you could just redefine the height. It's like way down here below. Yeah, sure, that would change the potential energy. You might like double it approximately. Right. But again, if you set up equations, then you get the same answers at the end. Right. As long as you define the floor at some height and you stick to that definition. So I can either define the floor here and it falls through the hole or not. If it does fall through the floor, through the hole, it can have a negative height. Right. Or it can define the floor way down here and maybe just always has like a crazy positive height. Right. As long as they're consistent with that. Okay. Another thing this sort of relates to, this is going to kind of tie into, but also doesn't make a here. Take a look at that G. You guys see that lowercase g? Now you guys know on Earth that's either 9.8 or about 10 meters per second squared, but it's really only true at the surface. You guys remember that from the last few weeks, which is if you tunnel down into the Earth, the closer you get to the center, the closest this number gets to 0 meters per second squared for G. Right? And if you take off in a rocket and you leave the Earth, that number also dissipates with the inverse square law the further away you get from the Earth. Okay? So this is really only true at the surface of Earth, isn't it? Okay? That's why I said localized. Okay? Let me get like a bigger perspective. Okay? Let's look at the entire Earth here. Okay? Here's the entire Earth. Okay? Let's think about probably the biggest height change you could have. Suppose you go into like the top of Mount Everest, okay? and you drop something from the top of Mount Everest and like you throw it over the edge and like lands into the ocean or something. I don't know if it really makes sense, but let's run. Okay? Well, just look, think about that height change. Okay? Now my picture is not to scale at all. Like height of Mount Everest is like tiny, tiny, tiny compared to the radius of the Earth. So my picture is greatly exaggerated. But even if this were true, look at this R2 compared to this R1. Okay. See how they're almost the same thing, top of Mount Everest to bottom of Mount Everest? Like the difference is, like, here's the height, which is the difference between R1 and R2. That's a very tiny difference, isn't it? Right? And what I'm trying to get at is that there is a bigger, more universal form of potential energy. Now, I think I'll probably save the story for tomorrow, but here's the answer. It ends up being negative G(m)m over R, where R is the distance to the center of the planet, m might be the mass of the planet, and little m is the mass of whatever object you're looking at, right? It is a negative value, right, which is weird, but again, I'll save that story for tomorrow. Okay? But it turns out that if you have two radial values, like top of Mount Everest to bottom of Mount Everest, that are pretty close to each other, right? And you just run two different R's, like R1 and R2, and take the difference. Okay? Turns out that the difference is exactly that right there, just MGH. That's all it is, just MGH. Okay? So far more often than that, maybe all the time, maybe 95% of the time or more, we're just going to use MGH for potential energy. But if you want to do something like solve for escape speed, like how fast you have to go to the moon, then you actually have to use this more universal form of potential energy, which again, we're not going to use very often in this class, but probably tomorrow at least, it'll come up. I'll tell you guys a little bit about that. Okay, you guys okay there? Okay. Now, for completion, I want to draw a graph for this situation because that's also going to segue to the next type of energy. Right? So let's do a graph for lifting the book, and the graph I want to do is going to be force versus height change. So lifting a book. Right? Let's say the book was on the floor and you lifted it, and you put it on the shelf. Okay. And we're saying what is the force of lifting it in newtons as a function of how high you've lifted it in meters, right? Okay. So you lift the book up 3 meters, right? And if the book had a mass of 1 kilogram and therefore a weight of 10 newtons, didn't you have to apply 10 newtons of force lifting the book, 10 newtons of force for the, oh, whoops, I double counted my unit. You guys got the idea. Newtons, meters, the whole day, right? Okay. This is a constant force, isn't it? Right? As you lift the book, it's pretty much going to be a constant force, right? And if you lift it 3 meters, okay, you guys see many graphs in this class. You guys know that graphs can get different properties of graphs can tell you things about different physical quantities. You guys remember 1 joule is the same thing as 1 Newton times 1 meter, right? Hey, newtons and meters, those are the axes on this graph. Therefore, if you multiply those two together, doesn't that say something about the area of a shape? You guys see a big old rectangle right here? Isn't this just force times height, which is the same thing as mgh, force times distance? You think of force times distance, force times height, mgh, it's all the same thing, isn't it? Right. Okay, so potential energy or the work lifting it, it's all the same idea. Okay. All right, now we're gonna pick up from there because I want to do a different type graph for a different type situation. We're gonna switch over to springs now. Okay. And in fact, I've got a spring right here. So all I have to do is unscrew this ball point 10, okay, and then take this cartridge out. And you guys see a spring right there? Spring. Right. Right. And I can take this cartridge and push it into the spring. Right. In fact, doesn't it take some work pushing the spring? Right. Okay, because I have to apply a force for some tiny distance, maybe about a centimeter. Force times distance. Ooh, force times distance. So I'm like transferring some energy into the spring. Right? That energy is stored in the spring right now. I know it's stored, and I can get it back out if I just release the cartridge. Right? So I might get it out by aiming straight up. Pow! Right? It's gonna fly out upward. Right? Okay, so that'd be like going from transferring from the spring back into that gravitational potential energy, wouldn't it? Right? Starting to think about conservation of energy. Right? Or you know what else you can do? Maybe more simply is just hold it horizontally. Right? Here, stop running to this guy. It's not really going to move. Right? Right? And then compress it, and then let go. Right? So it went from being in the spring to like energy of motion, right? Which is like having a speed, which is like kinetic energy. I haven't quite gotten it to in the notes, but you guys can think ahead a little bit, right? Right? So there's definitely energy in that spring. Now, how much energy? So, and what could this be called? So this is also a type of potential energy, but I'll call it spring potential energy. Spring potential energy. Okay. And the symbol for that is, it's also going to be U for potential energy, but I'll throw a little subscript S on it. Right? Or if you see PE sub S, I guess, right? Something like that. Okay. This could be energy stored in a spring. Right. Now, think about energy stored in a spring is, remember, you're pushing with some force for some compression distance, but that force is not constant. Like lifting a book, the force was constant, but that's not true for a spring. And you remember that because you remember Hooke's law. You guys remember Hooke's law? Okay. Hooke's law, okay, which told you that compressing a string or a spring, compressing a spring or stretching it. You guys remember F equals KX? So if I had a graph and I put force in newtons on the vertical axis and how much it's compressed or stretched for that matter, okay, on the horizontal axis, okay, then say not stretching or compressing at all, that would require 0 force, but then it takes off in a linear relationship. Okay, so if I compress it 3 times as far, it's going to take 3 times the force. Okay, if I compress it some general amount x, then it's going to require some force, which is equal to k times x, right? Where, see if you guys are following here, right? This line has a slope, rise over run. Right? What property of the spring is the slope of that line? It's a spring constant, isn't it? You guys see that? Right? Okay, right. Like here's your x, here's your f, right? That's like x and y, right? The slope is like k, it's it, right? That's how stiff the spring is, right? Let's do some examples here. You guys got different kinds of spring scales. Remember the brown ones are like the most versatile, the kind of medium stiffness. Ooh, it's kind of stiff, but I can pull that, take some number of newtons to stretch it so far. Okay. The gold ones, oh, those are super stiff. You guys know that? It's like, it's a lot of force, really hard to stretch that. Ooh, right. So suppose the line I drew is like for the brown scale. For the gold scale, it's a lot of force just to stretch it a little bit. Okay, wouldn't that be like line like that? Okay, it takes a lot of force to stretch it just a little bit. Okay. And the green scales, that was like really small spring constant, hardly any force at all. Put a tiny force and it stretches a lot. Okay. So that'd be more like for the green scale, right? Put a little force and it stretches a lot. So here's the green scale, the brown scale, and the gold scale. You guys know that? Okay, the different spring constants. Okay. But you know what? Very similar graphical story to lifting a book in that the area under the curves still some quantity of joules, okay, which tells you how much work it took to compress the spring and also how much energy is still stored in the spring. So if I take the area of this triangle, right, then that will tell me what the spring energy is. Okay? So wouldn't it be 1/2 base height? And the base of this triangle is x, and the height of this triangle could be kx, right, from Hooke's law, right? So the energy, this is the energy stored in the spring, is the area of that triangle. Okay, and I can quantify it 1/2 base height because it's a triangle. Okay. Hey, those x's I can combine, and that gives me the energy stored in the spring is 1/2 kx squared. Just like that. Right? Sorry. Let's run an example. So for example, okay, let's say that the spring constant was like 3,000 newtons, and the amount you compressed it was like 10 centimeters. I could also call it 0.10 meters. That'd be true. Okay. So the compression distance, square that, or stretch or compress, square that. Okay. Multiply by the spring constant and divide by 2. So it's 1/2 times 3,000 times 0.1 squared. Okay. And that gives me 15 joules. Let's say there's like 15 joules of energy stored in that spring. Right. It also takes 15 joules of work to stretch or compress it to that point. Okay, is that right? Okay, guys good? All right, so we got one building block to go, okay, and that's going to be energy of motion, kinetic energy. Let's go back to this big old checklist. Okay, so we did that. That led straight to this. That also fed pretty well into this. Okay, we just got to hit this guy, right? And then remember this guy on the very bottom. You won't see very often in this class, but it's more universal form of this. Okay, so here's our last one, last building block, okay, kinetic energy. Okay. So kinetic energy. This is your energy of motion. So if something has a speed, a velocity, okay, capital K I've been using for kinetic energy. If you see some of my old materials, you might see KE. I think Paul Hewitt also uses KE, right? So you might see, right? Okay. And you know, I'm just gonna start out by giving you guys the formula for this. So the kinetic energy is 1/2 mv squared, okay? Where m is the mass of the object, v is the speed of the object. Okay? Notice I'm saying speed because I think I forgot to mention, but energy is a scalar quantity, so it doesn't matter the direction of this, these things. Okay? Now, I've tried to find a derivation for this. There's probably one out there somewhere. I've never seen one in a textbook, but here, give you guys a couple of explanations of why this formula works. Right. One is that when we actually apply equations and start solving for stuff, you'll see that if you apply this, all the numbers just work out. You get answers that we did like back in the past, you know, for using different other techniques, right? Kinematic motion. Right? But you know, if that wasn't good, then I think maybe this sort of works. Right? A topic we're going to talk about in the future is momentum, and momentum is mass times velocity. Suppose I look at the momentum of an object as a function of its speed. Right. So this could be in kilogram meters per second for momentum, and this could be meters per second for the speed. Okay. Well, this would have to be like a direct relationship because if it has like 3 times the speed, it would also have 3 times the mass times its speed, right? We'd have to, right? The slope of this line is just the mass of the object. Right? But it turns out that the area under this curve also represents some number of joules, which is energy. Okay? So the kinetic energy area of the triangle, 1/2 base height is 1/2 mv squared. There you go, kinetic energy 1/2 mv squared. Let's do an example. For example, suppose you had a mass of, say 1 kilogram, and it was going at 10 meters per second. Right? 1 kilogram, this guy going at 10 meters per second. Pretty good speed. 10 squared is 100, divided by 2 is 50. You're looking at 50, and the unit would be joules. So the 50 joules of energy associated with, say, this object moving at 10 meters per second. Okay. Is that right? All right. No, I want to do one of these scenarios with you guys before you take off today. Right, let's look at the first one. Right. Galileo drops the ball from the Leaning Tower of Pisa. Hey, isn't this the scenario you guys have seen over and over in this class? It keeps recurring, doesn't it? Hey, it's really classic example for what we're starting today, conservation of energy. Okay, so each of these scenarios, I want you guys to identify what's in the closed system. There are a couple of open systems. We'll talk about those later. Okay, what's the energy mix at point A, at point B, and then you can equate those because of conservation of energy. Then you can solve for stuff. For example, you could solve for the speed at point B. Okay, not the only thing you could solve for, but it's one thing you could solve for. So let's try that. What is in the system? I definitely care about the ball. Okay, the ball is being dropped. I'm going to focus on the ball. But guys, that ball has a force, and that force is its weight, and that weight is being provided by the entire Earth. Okay, so Earth is like the other object in the closed system. Okay, the ball Earth, you can call this the ball Earth system. You call it like that. Okay, and then now it's a closed system. Okay, energy at point A. Well, Galileo had to lift the block up the Leaning Tower, so it had to do some work lifting it. So now it has gravitational potential energy, MGH. I'll put a little subscript A on that H. Now notice that Galileo just drops the object, right? He doesn't like chuck it down. He doesn't throw it, which if he did have to put a kinetic energy term here too. He just drops it. Okay. Then the ball falls, and right when it's about to crash land, it has a huge speed. So at point B down here at the ground, it has some 1/2 mv squared. I'll throw a little subscript B on that V. So we've got point A and point B. Okay. But that's all it has. See, it doesn't have any potential energy at the bottom because it has 0 height. Maybe like 1 millimeter above the ground, but basically 0 height. So it has this energy mix at point A, this energy mix at point B. Now we can use this to solve stuff, like for example, the speed at point B. Let's do this real fast. So sum of energy at point A is equal to the sum of energy at point B. It started off with all mgh at point A. It ended up with all 1/2 mv squared at point B. Okay. Suppose you're solving for the speed at B. Do you guys see the mass is going to cancel out? Wasn't that like the point of the Galileo experiment? So the mass cancels. Times 2 VB squared is 2GH. Square root, speed at point B is square root 2GH. Okay. Now, I know I gave you guys like a tiny little quadrant here. Can you guys probably write that proof right there? Okay. And you know what? You guys have seen this before. You guys remember these kinematic equations? We already solved this problem in the past. Here, suppose Galileo drops the ball. Isn't initial velocity 0? If you solve for speed at the bottom, find out the speed. Isn't just the square root of 2ax? But A, well, that's lowercase g because g is a special kind of A. And x, displacement, well, it's like the height change. So that is B final is the square root of 2gh. It's the same thing. So you guys already have a method to solve for this, but this is just a different way of approaching it. In fact, the new way of approaching it is it's going to give us some advantages too. Okay. You guys get that? Okay, so you guys can copy this, write that quadrant, right? And then we'll do some more of these examples tomorrow. All right, you guys have a great rest of your Monday.